So, okay. So welcome everyone to this ICM invited lecture. I am Balint Tóth from the University of Bristol and from the Rényi Institute of Mathematics in Budapest. And it is my privilege and honor to introduce Patricia Gonçalves from Instituto Superior Técnico of the University of Lisbon, who will deliver this talk. Patricia contributed substantially to the mathematical theory of time-dependent phenomena in statistical physics, and in particular including hydrodynamic limits and fluctuation fields of interacting particle systems, which is the name what probabilists call these physical systems. And about this, we will hear more details just in this lecture to come up. And thank you very much. And I'm looking forward to Patricia's talk.
Welcome to the third lecture of today. We are very pleased to have Patricia Gonçalves here. And to speed up things, no introduction. Her topic is on the hydrodynamic limits of fractional PDEs from stochastic interacting particle systems. So please go ahead.
Thank you. Thank you so much, Yanni, for the introduction. So first of all, I would like to thank the organizers of this conference for allowing me to be here and give this talk in person, which is very nice after these 2 years of the pandemic. I really enjoy it. And what I decided to do is to overview some results that I have been obtaining with a group of collaborators that I'll show you. This is, well, probably you know some of them. This is people that I've been working with over the last years on problems which are related to what I will present here today. And I hope to be able to do everything I want to talk about. So let me just give you the physical motivation for the problem that I will present. So suppose that you want to, let's suppose that we have some continuous space. So in my talk, I will always be talking about the interval 0, 1. But imagine that you have, for example, this square here. And what we want to understand is how to obtain the macroscopic laws that describe the evolution of some conserved quantity by looking at the random dynamics of the microscopic system of particles. That's basically the idea. So the first thing that we should do is to find the equilibrium states of that system, so the invariant measures. Then we characterize them by the quantity that we want to analyze, this conserved quantity. So I call, okay, it's here. I call it, let's say, rho, which depends on the, let's say, which will depend on the positions of where I'm looking at. And so if I fix the, let's say, u in my space, so if I fix a point u here, and a small neighborhood, but a macroscopic neighborhood around that point, then I say that my system is locally in equilibrium. I assume that, and my local equilibrium is characterized by that quantity rho of u. Okay, rho that depends on the position that I just fixed. And then I say, okay, I have this local equilibrium at time 0, which is okay to assume because I have so many molecules that the system locally should be close to this equilibrium state. And then I ask exactly the same questions. I let my time evolve. So I fix the time t, and then I ask the same question. So if I look at the point u, I should have my system close to some equilibrium, which is now depending on both time and space, and I call it rho tu. And the question is, how can I deduce the evolution? So what is the equation that is satisfied by this function rho tu? How does it evolve? So what we will do is to give, let's say, to formalize this and to have this macroscopic description using the microscopic description of particles. So I will discretize this volume, so this that I called lambda, according to some scaling parameter n, and I will call the discrete size, the discrete space lambda n. I will have two scales for space and time. There will be a discrete, let's say, there will be a microscopic time. I will need to give time for particles to move around in terms, let's say, of order n, because I want things to be non-trivial at the macroscopic evolution. At each, so I will have two scales for time. I have two scales for space as well. So there will be a microscopic space and a macroscopic space. And in this discrete space, at each site, I will put a certain number of particles. and the dynamics will conserve some quantity. In the models that I will show to you, all the particles, they will be, let's say, evolving according to exclusion rule. So this means that at each site of my discrete space, I will allow at most one particle. So this means that if they want to jump to any other position, but the position is already occupied, the jump is suppressed and particles have to wait a new random time. So these will be Markov processes, so they have this property of the memory loss. If I want to know the future, a condition to the past, I only need to know the present. So the question is, what is the microscopic law describing this conserved quantity for my system? So for SEP, so the symmetric simple exclusion process that I will review just in a couple of slides, it is known since a long time ago that one can obtain the heat equation on the torus, on the interval, on the line, even more complicated domains, and also with boundary conditions. So, and what I want to talk, so the aim of my talk is to give an overview on how to obtain not the heat equation, but to replace the Laplacian operator by some fractional Laplacian, but also restricted to bounded or unbounded domains. I hope to have time to talk about unbounded domains at the end. And how to obtain boundary conditions from the microscopic system. And what type of boundary conditions, then I will explain. And as well, we want to see how to put some, let's say, some local defect in the system. So for example, by slowing down a rate between two consecutive sites, what does it happen at the macroscopic level? Okay, so that is the goal of the talk. Okay, just to formalize it, so imagine that here, so here is just a picture so these clocks here, the only thing that they are doing is to say the following. At each pair of sites, let's say X and Y, whatever they are, because I want to allow long jumps in my system, I have a Poisson process. So, okay, so these clocks, what they are saying is that every time I see a mark of one of these Poisson processes, particles exchange positions in the sites where I'm looking at. So I will have, as I mentioned before, I have a scaling parameter, which is this parameter n. I will have a space, so typically here my macroscopic space is the interval 0, 1, and the microscopic space is just, okay, let me probably make a picture. I have the interval, 0, 1. I split it into little intervals of size 1 over n. So this is my space lambda. And now I have the particles evolving from 1 up to n minus 1. Okay? And there will be a time, a microscopic time, so I use the letter t theta n because it will depend, so the choice of this time scale depends on the type of the dynamics that I have behind. The macroscopic time will be denoted by t. And I have this Poisson, so let's say the clocks, the jumps, the particles have to wait for a time which is given in terms of these Poisson processes, which are independent. There will be this transition probability P. So let's say a particle can jump from a position X to a position Y, which will be given, so this rate will be given in terms of this P, which only depends on the size of the jump, okay? It doesn't matter from if I'm jumping from X to Y, it only matters the size of the jump, and then I will tell you exactly what it is. So eta t of X will denote the number of particles at X, but since I'm going only to consider exclusion processes, this eta will take the value 0 if it's empty, or 1 if the site X is occupied. I have Markov processes, so I have all this machinery that Thierry just mentioned, so all these martingales, it will appear in my talk. And the density will be conserved, okay? Because particles are only moving around in a discrete space, and the density is conserved. But I will destroy this conservation law by adding reservoirs, and the goal is to understand how the reservoirs destroy the conservation law and what is the PDE associated to this density of particles. Okay, so now this is the dynamics. So when you see, I'm not sure you can see, but there is some arrows here in blue. So this means a clock is ringing. So it means that the particle can jump from this position to this position according to a rate P2. Since it's empty, this happens, okay? And well, this is not allowed, or you can think that it is allowed. Particles swap positions in exclusion, but since I do not distinguish them, if this jump occurs, it's the same as saying that nothing happened and particles have to wait a new time. And this cannot happen. So here you see two clocks ringing at the same time, but this happens with probability 0, so we neglect it. Okay, so just to give you an idea, I have some simulations here on the right side, and the goal is to do the following. I have a quantity which is the density of particles which is conserved. I will associate to it what is called empirical measure, okay, which is written over there. So what is this measure? It's a random measure. So eta here, I hope you can see the mouse, but here eta is a configuration. And this is just a sum of Dirac measures. So here, eta t of x is the quantity of particles at site x. So this measure is giving weight 1 over n every time I see a particle at a position x, okay? And then my question is, so if at time 0, I assume that this measure is converging, so the proper statement is the following. So if pi n 0, at my initial time, is converging to some deterministic measure, which is absolutely continuous with respect to measure with the density gu, which is some measurable function, is the same true at time t. So let me put it like this. And what is this? So this density here is the solution of which equation? Okay? So in the simulations on the right side, I have two different particle systems. So here, in fact, so when you see this, let me go here. So for example, in here, we start this initial configuration. Here we allow more than a particle per site. So for example, here what we have is 0 particles at position 0, 1 particle at position 1, 2, and etc. So this is my initial configuration, and particles just jump to the nearest neighbors with rate 1/2. Down, what you see is exactly the same dynamics. Particles just jump to nearest neighbors with rate 1/2, so symmetric rates. But here there are no particles between the site 0 and the site 20, and from 31 to 50, no particles, and here always 100 particles in this position. So what I want to see, so now I'm putting this in the simulations that I will run, you will see in black the microscopic, the random system moving around, particles moving around, and the shape will change, and the same thing down. And in red, what you see is the initial condition of some PDE, and we will see if they are close. So if the microscopic system is close or not to this line, let's say. So the question is, what is it? What is the solution of which equation? So there are several dynamics that one can define even in the extrusion process. So here in this rectangle, you can see, for example, then one can get the heat equation, as I mentioned before. So we have a P, which is symmetric, for example, nearest neighbors, jumps to left or right with rate 1/2. And the time that we have to speed up the system is the diffusive time scale, Tn squared. We can also get porous medium equation, and at the end I will comment a bit on the fractional porous medium, but here you see it's a Laplacian, but rho to the m. So here m bigger than 2, and an integer, for example, rho 4 or rho 5. And the fractional versions, so if we take now the derivative in time of rho equal to the fractional Laplacian, but now you see here that the p, there is a choice for p, I'm not sure everybody can see, but there is the p, so p of z is going to be a constant to make it a probability, divided by z to the power 1 plus gamma, and now I need to speed up the time as Tn to the gamma, and gamma between 0 and 2. And I can also get the fractional porous medium. So these are several equations. There are many others. So the only difference between these and these is like in the first case, you just replace the rho by some power of rho, okay? And I will explain, I hope to be able to do that today, is to tell you how can we get this, let's say, this fractional heat equation, but on bounded domains with boundary conditions, and also the porous medium equation with in some domain. Okay, and what are the dynamics that are behind these equations? Okay, so now, because I want to make it quite simple, so first I will try to explain the easiest case. So I will present this hydrodynamic limit, this result that I just mentioned over there, for an exclusion process that I will put in contact with reservoirs. So the reservoirs will inject and remove particles in the system, which means that the number of particles is no longer conserved. And I will allow particles to give long jumps, and the p, this probability that I showed you before, so this probability here, I will distinguish two cases. The first case is when p has finite variance, which means that the choice for gamma will be bigger than 2, and in that case, what I what I see at the microscopic level, I see long jumps, but which are being done with very low probability. But at the macro level, I see exactly the same equation as I see as if it was nearest neighbor, so just the heat equation. When I take P with infinite variance, so I start to take my gamma between 0 and 2, and then we will distinguish two cases, then I see something different, okay? Then I will start to see the fractional heat equation. So let's start with the easiest case. Let's see what happens when I have just nearest neighbor case, okay? Just jumps to nearest neighbors. I have my microscopic space as the interval 0, 1. The discretized space that I called lambda n, the set of points where I put the particles, and the state space of my Markov process is just going to be 0, 1 to the lambda n, because I only allow at most one particle per site. Okay, the dynamics is like this, and I will try to, there are a bunch of parameters, but I will try to explain the role of all these parameters. So here you see some blue particles at the end, and what they are doing is to, let's say, to mimic the role of reservoirs, okay? So here in the bulk, what we call the bulk, so my space now, what I'm doing in this picture is that I'm adding here the site 0, and I'm putting the blue particles, I have 2 over there, and I'm adding here the position n, where I put 3 particles. So these are playing role of reservoirs, and in the bulk, so the set of points from 1 to n minus 1, I just allow at most 1 particle, and they jump, in this case, to nearest neighbors with rate a half. Okay, so that's the dynamics in the bulk. Now at the boundary, what happens? So there is a parameter, okay, maybe it's better to go here. There is a parameter here, which is theta. So this means that, okay, there are 2 differences first with left and right reservoir. There is an alpha and a beta. So what is this doing? So first let's see alpha very close to 0 and beta very close to 1. So this means that so alpha equal to 0 means that I am not injecting many particles from the left reservoir, and beta equal to 1, I'm injecting a lot of particles from the right. Okay, so alpha and beta, they tune the density reservoirs. That's the idea. And if they are different, there is a current which is being induced by the reservoirs on my microscopic system, on the bulk. And then we say, okay, so that is clear what these parameters are doing. What is theta doing? So theta over there, it means that if theta is positive but very big, the rate to inject or remove particles is very slow. So the boundary dynamics is very, very slow. But if theta is negative, it means that the dynamics is very fast. So there is an interplay, there is a continue or, yeah. So there is a balance between boundary and bulk generators. And what we want to understand is how to change the value of this parameter theta. What does it happen at the macroscopic level? Okay, so theta negative, so keep in mind that theta negative, the dynamics at the boundary is quite fast, and theta positive, it's very slow. Okay, and we'll see if there is any transition. And the role of kappa now, because there is a kappa over there in red, and the idea of this kappa is that sometimes we do not know what is the PDE or the boundary condition that we want to observe, and sometimes this kappa can give us some intuition of what to search for. But I will comment a bit on this later on, okay? So I hope it's clear, the dynamics. So okay, so what should we do now? Now that I defined my dynamics, I have to first understand what are the equilibrium measures. And when I have the alpha and beta equal, so it means that the density reservoir, so there is no induction of current by the reservoirs because they have exactly the same density, the Bernoulli product measures, they are invariant. And these are exactly the same measures let's say the same invariant measures as if we didn't have any boundary dynamics, just exclusion dynamics. Okay, now we say, well, but if alpha is different from beta, and there is this difference of density at the reservoirs, these measures are no longer invariant, but we know that we have one continuous time Markov chain, which is irreducible with a finite state space. So there exists a unique invariant measure, which is usually, people call it the NES, the non-equilibrium stationary state. And describing the non-equilibrium stationary state is something that we don't know, even for this easiest system, just nearest neighbor, exclusion with rate a half, and just alpha different from beta. It's not known. But there is a method which was introduced by Derrida and many of his co-authors, which is called the matrix ansatz method, which means that basically you can write this non-equilibrium stationary state in terms of products of matrices that obey a certain algebra, and from that matrix, let's say from this matrix ansatz, you can recover some properties about this ness. But I will not rely on this because in the long jumps case, this method doesn't work. In fact, this method is very restrictive. Even if you just ask two particles at the same site, it doesn't give any information about the ness. So I will not rely on that. And in fact, we don't need it, so we don't need to know what is the ness. So I will tell you why a little bit later. Okay, so what is the goal? So as I said before, the goal is like this. So we associate to the conserved quantity, which is not conserved anymore, but it's the density that we want to analyze, this empirical measure written in this way, exactly as before, and I speed up the time by n squared, okay? And I will explain later why we do this. So we assume some condition at initial measure. Basically, what we assume is that this result is true. So a law of large numbers is true at initial time. Now we have to be a bit careful because this measure here, it's a random measure. And I'm saying that it converges to a deterministic measure, but I need to say in which sense. So what you see in this first rectangle here, so what I do, I take a test function, I take a function h, which is continuous, on the interval 0, 1. And what is written on this left side is just the integral of h with respect to the empirical measure. And since it's a sum of Dirac measures, you just obtain this sum here. And we are saying that it converges, in the weak sense of measures, to this measure here, which is gq dq, which is the measure that I wrote over there, deterministic, absolutely continuous with respect to the Lebesgue measure with this function here, g. And then this is usually, okay, this is a convergence of measures, but I still have randomness here. So I have to say that this convergence is true, I assume it is true, in probability with respect to this measure mu(n), which is my initial distribution of my system. So I start the system, I start eta 0 with this distribution mu(n), which I say that satisfies this condition. And then the question is, well, if this is true, this is what we say mu(n) to be associated to the profile G. Is this true for any time t? So is it true that pi nt converges to this measure here, but now rho t is a function that depends on time and space, and it evolves according to some PDE, what is called the hydrodynamic equation, okay? And of course that this convergence here now is with respect to distribution of the system at time t that I call mu(nt), okay? Okay, so let me just recall the first result for the exclusion process, symmetric exclusion with reservoirs. So the reservoirs, as we discussed before, so beta over n theta with k and so on, and alpha, and etc. So so this was proved by some colleagues in Brazil, and the result is the following. So if you take a function g, just measurable, which is the initial condition of my PDE, and it is the function for which I assume that this convergence is true. Okay, so if I fix this function, then I say, okay, I have the convergence at any time t, so here it is the result, the weak convergence of measures, and rho t is the unique weak solution of the heat equation that you see here, so the derivative in time equal to times the derivative in space, with initial condition g and with different boundary conditions. So let's see, so here for 1, oh, it's back. So for theta bigger than 1 means that, so theta is positive, so the system is very slow. For theta bigger than 1, the reservoirs are so slow that at the macroscopic level, what I see is the heat equation with Neumann boundary conditions. So the derivatives are equal and equal to 0. For theta equal to 1, and this is the case in which both the let's say, the impact of the bulk dynamics and the boundary dynamics gives a non-trivial contribution at the macroscopic level. So what we get is linear Robin boundary conditions of this form. So this means that the derivative in space of the profile is proportional to the difference of concentration of rho 0, so the concentration inside the bulk, and the boundary reservoir, the alpha. Okay? And you see here that k is appearing. Remember this parameter k that I said in the beginning that would be important, okay, which is written here. There is k times beta. It only appears in the Robin case, and I will comment why it is important. But before that, let me just say that for theta less than 1, so reservoirs are slow or fast or quite fast, what we see is Dirichlet boundary conditions. So we really see the profile being fixed as alpha and beta at the boundary. So here it's clear everything is known, but imagine that we didn't know what happened for theta positive, or for, imagine that we knew this regime here with a k, but we didn't know one of the regimes. So the question is, how could we figure out what we would like to obtain? Here it's simple, but in the long jumps case can be quite tricky. So now the k plays a role. Imagine that you naively come here to the equation and you say, okay, I want to take k equal to 0, so I should see Neumann boundary conditions. And now I take k to infinity, and the way to give sense to these equality is to say that rho t0 is equal to alpha. So by tuning the value of k at the level of the Robin conditions, at the Robin boundary conditions, you can see the other two equations that you are looking at. Of course, that there is an interchange of limits, so this is just a naive way of justifying what we expect, but it is a way to try to figure out what is the boundary conditions that we want to see. Okay? Okay, so now, one question that one can ask is the following. I ask my initial measure mu n, to satisfy this condition. So we prove the result, so they prove the result. They say that for any measure for which this is true, hydrodynamic limit is proved, but the question is the Ness included here? Is the stationary measure satisfying this condition? And this is what is called the hydrostatic limit, which they proved as well. So if you start from mu SS, the non-equilibrium stationary state, what we have to show is that this stationary, so let's say this mu SS, this Ness, is associated to some function. And what is the candidate for this function? It's just a stationary solution of the equation, okay? Which in this case is quite simple because it's the heat equation. And we have different, so it's these three different profiles, which is just the heat equation, but depending on the boundaries, you see different profiles, okay? Okay, so this was done for nearest neighbors. And how does the proof goes? And then I will try, Thierry already talked about this today. So the proof goes by using the entropy method, which was introduced by these authors here, by Guo, Papanikolaou, and Faradan in the 80s. And the idea is to show that there is tightness. So you can prove weak convergence through subsequences, and one has to characterize the limit point. And this is mostly the most important part, so it's the one which I'll focus on. So we have to show that the limiting point, we call here Q, is in fact a delta measure on top of a trajectory of measures, which are of this form. So PQ is absolutely continuous with respect to the Lebesgue measure, and rho TQ is a solution to the hydrodynamic equation, okay? So this is the goal, how to characterize the limiting point. Once we know it is unique, we have the convergence. So one of the important things when we start to do this, to play these games with the particle systems, is that sometimes you get to notions of weak solutions, which are not exactly the notion of weak solutions that people have in the PDEs literature. And sometimes, uniqueness is super important, as I mentioned before, because you really want to have the convergence. So sometimes you have to ask some regularity of your solution, ask properties of the solution to get uniqueness at the macroscopic level, but then one has to obtain these properties from the microscopic system. Okay, I will explain this to you in a couple of minutes. Okay, so let's go. So in the case of, so let me probably write here. So when we are in the Dirichlet case, so now I have the heat equation, and I have the Dirichlet case. So this profile is equal to alpha at 0 and equal to beta at 1. There are two different notions of weak solutions, and let me tell you why this is needed. So I put here the first notion, which uses as test functions which are C1 in time, C2 in space, and the 0 there means that they take the value 0 at 0 and 1. Okay? So the first notion of weak solution that one can derive for this system is this one. So the profile lives in some Sobolev space. We need some regularity. And when you take a function which has this condition, which lives on this space here, we have this integral formulation. Okay? And here in the equation, okay, maybe I go here. It's important because you already see let's say the parameters alpha and beta in the equation, which is here, alpha here and beta here. Okay, so this is one notion of weak solutions that one can get. But there is another one, which is this one. So imagine that now you need to test, by some reason, with a smaller space of test functions, like, for example, functions of compact support. And if you do that, so you see that here, for example, these terms will disappear, and you wouldn't have uniqueness of your weak solution. So you need to require something more. Okay, as before, we require some regularities. The profile lives in some Sobolev space. Now you test against functions which have compact support, and then you don't have uniqueness. So you need to add something to your equation to have uniqueness, and then you just ask that your profile has exactly the Dirichlet conditions almost surely in time. Okay? So this is another notion of weak solution for exactly the same equation, heat equation with Dirichlet boundary conditions, but we need something else. Okay? So, and all of these that we require for the macroscopic solution has to be derived from the particle system. So we have to have a way to deduce all these conditions from the microscopic system. Okay, how this is done? So let me now use the machinery of my martingales. And the idea is the following. You analyze, so we have a Markov process, we have an infinitesimal generator that I'm denoting by Ln, and we see how this infinitesimal generator acts on the empirical measure. So this is okay, it's a bunch of computations, but let me just explain what is important. So this is just the integral of a function h with respect to the empirical measure. You expand it, you have these. And now you see here that, for example, if your test function h is 0 at the boundaries, which is something that we require in one of the notions of weak solutions, then you can just erase or forget one of these n's and convert it so you can subtract h of 0, convert this n times the difference into a gradient, and you have an n to the minus theta in front of it. So if theta is positive, this term disappears, and this term disappears. So this is what I do here. I hope you can all follow me. So I'm here now. So I converted this into this discrete derivative, okay? But I pay a price of order n to the minus theta, which is fine if theta is positive, so I can use this space of test functions, and then okay, there is something to do. Let me just explain more. I have to be able to replace this eta 1 by alpha because I want to recognize the Dirichlet conditions. And this is something that it's true. We can replace the eta 1, and this is what is called the replacement lemmas, which I will comment a bit at the end. And then you can rewrite the martingale in this way, plus a price of order n to the minus theta, which goes to 0 for theta positive. And then you immediately see that if you assume the local equilibrium, so if you assume that you take the expectation, so expectations of this martingale is 0, and what you get is exactly this equation which is written here, which is the notion that I wrote before. So if you can compare this with what is written here, it's exactly this integral notion for the weak solution. Okay, so what are the important ingredients is that I use the correct space of test function so that I can see the limiting equation, and I need to have some replacement lemmas which allow me to replace eta 1. So the boundary, let's say eta 1 is the quantity of particles that I have at position 1, that I have to be able to replace it by alpha, and the same thing at the right. Okay, what happens now if I take theta negative? That error blows up, we know. And so we cannot take functions which are just zeros at the boundaries. We need to take a smaller space of test functions. So we take functions of support. If we do that, these two terms disappear, and we get exactly the notion that we had before. But as I mentioned, this doesn't give uniqueness to the PDE, so you need to require that the profile really satisfies the Dirichlet boundary conditions. Okay? We need to prove that the profile satisfies these conditions here. Okay? So now, let's mess it up. Let's do the following. Let's imagine now, okay, I didn't draw everything because it's quite big, but imagine that for in Z minus, you have at each point of Z minus a reservoir, which is injecting or removing particles everywhere in the system, according to this probability P that I mentioned before. In the bulk, everybody can jump to everybody, okay? Can jump to any position, so with this P again. And on the right side, you also have at each position to the right side, from n to infinity, you have also reservoirs which are injecting and removing particles exactly with the same rates as before. So you still see okay, here you see there is an alpha, there is the kappa, and there is the theta. And if you come from the right, you replace the alpha by beta. Okay? So it's exactly as before, but now long jumps are present everywhere. Okay, so the first So the choice for P is, as I mentioned before, you have PZ given by this expression here. So the size, the P depends only on the size of the jump. C is just a normalizing constant to make it a probability. P is symmetric, and it has mean 0. And by now, I will go quickly over this because I know my time is almost done and I'm in the middle. So if you assume gamma bigger than 2, it means that the variance of P is finite. So this means that I can give long jumps, but these long jumps, they have very low probability. And what we obtain at the, let's say, so let me just go here. So this is a summary, let's say. What we obtain at the macroscopic level is exactly what we had before. So we have the heat equation that you can see over here, as before. Okay, now there is this factor in front of the Laplacian, which comes from this variance of P. It's this factor here. For theta equal to 1, we have Robin conditions as before. So there is the K here. Okay, there is an M here, which is the first moment of P, which is just the sum of a Z. So, okay. PZ, which is finite. Oops. So we have the Robin regime, which is here, so for theta equal to 1. So this is just a picture to say that in the vertical axis you have the value of theta varying from theta equal to 0 to infinity or theta negative, and here it's the gamma. So we have Raman boundary conditions, Neumann boundary conditions, Dirichlet boundary conditions, but here in this line, it starts to appear the heat equation with a reaction term, which comes exactly from the boundary dynamics. So it's this equation that you can see here. So there is the heat term, and there is this reaction term, and here down, we just see the reaction equation, which is this one. So here, basically, we change the time scale in such a way that particles do not have time to diffuse, and what we see is only the contribution from the boundary dynamics. Okay, but everything here, everything down here has Dirichlet boundary conditions. Okay, so these are the 5 PDEs that we get in this regime. And now what we want to analyze is what happens when we start to ask P to have infinite variance. So, okay, just a picture about the stationary solutions, but I will skip. So let's start, for example, to look at the case where gamma is between 1 and 2, and then I will comment a bit on the other case. So in this case, what we are going to replace the Laplacian operator by this operator here that is called L, okay, I denote it by LK. So in this case, I'm looking at the regime θ equal to 0, so the regime that we have both contributions of the boundary and the bulk dynamics at the same level, with the same contribution. So there is a reaction term here. There is another reaction term here with this KV1, and V1 are exactly the functions that I mentioned before. Let's say they are they are coming from the contribution from the boundary dynamics. And there is this operator here, is what is called the regional fractional Laplacian, and I will show you in a moment, okay, immediately now, what is the definition. So just quickly, imagine that you are defining, okay, just the usual fractional Laplacian in R. So it's an operator that we define in this way. So there is a constant here, C gamma, but forget it. It's just the limit as epsilon goes to 0 of this integral here. And this is true, okay, whenever this limit exists, and we have to ask some regularity on these functions. So this is usually one of the definitions for the fractional Laplacian in R, and what we obtain is in fact the same definition of this one, which is called the regional fractional Laplacian. That the expression is given like this: L of h is just the integral, but now you integrate in your domain, which is for us the interval 0, 1. So you have here the same definition as for the regional fractional Laplacian in R, but for the fractional Laplacian in R, but now restricted to the domain 0, 1. And there is a relationship between the two, so you can look at this identity for functions of compact support, and this is the operator that we obtain. So we, let's say, replace the Laplacian operator by the regional fractional Laplacian operator. Okay. The regularity. What about the regularity? So before I say that for the heat equation, the profile was living in some usual sub-Left space. Here it lives in some fractional sub-Left space. I will skip this, but just to say that this is also possible to prove this regularity from the particle system. And okay, I'm going to get a lot of equations, but just let me tell you one equation that we get, which is this one. So in one case, for gamma between 1 and 2 and θ equal to 0, we can obtain a weak solution of a PDE which is this PDE here with Dirichlet boundary conditions. And the notion of solution is this one. So we need to take test functions of compact support. We have this integral formulation, and we need to show some regularity about this profile. Okay, but I'll skip because this is technical. I will skip this as well, just how to go from the martingales micro level to PDEs macroscopic level, so I will skip it. But let me tell you, so what I have described, the equation that I have described is the equation that we have here on this brown line. So we have this, let's say this equation here, with Dirichlet boundary conditions. But now the question is, okay, so from here to this side, it's already what we had seen before. So this is gamma bigger than 2. This is gamma between 1 and 2. This is the reaction case. And now the question is, well, but if I take theta positive, what do I get in my equation? What is the equation that we get? Okay, so this was puzzled us for a long time. And the idea, so this is why K plays a role. And it's like this. So if I'm looking at the equation here on this line, which I showed you before, it's here, and it depends on K, you can ask that, well, maybe... Oh, what? Yeah, good. So if I take K to 0, what should I get? Should the limit of that equation that I get here be the solution that I have here, very close for theta, very, very close to 0, but positive? So that was so in fact we can prove that if you call rho k the solution of that equation, that rho k converges to the two equations that we get. So let's say the equation with the reaction equation and the new equation, which is what we call rho 0, which is basically you go to the equation that we get before and you take k equal to 0. And then we said, okay, so maybe the equation that we are searching for in here, in this regime that we don't know, it's exactly the equation that you have here with taking k equal to 0. Well, but in that case, it has to have Dirichlet boundary conditions. And this was quite puzzling for a time. And finally, we have all this zoo of equations. So let me tell you, explain more or less this graph. So here, this is the case we have seen before. This is always a reaction equation. Here in this line is this reaction diffusion equation with the regional fractional Laplacian. Here is exactly what I just told you. You get the equation that we got here on this line. You take k equal to 0, but you have Dirichlet boundary conditions. And here we start to see fractional derivatives, so fractional boundary conditions of Robin type. And here in this regime, you see fractional derivatives of Neumann type. Okay? So, okay, I will just skip these because, okay, the stationary solutions. Okay, so maybe here I have, what, 2 minutes? 3, okay. So let me tell you what is difficult here, because it's technical. It seems that what we need to prove is just go to the martingales and try to prove some limits. So the difficult thing when we try to get to all these equations, even here you see at the notion of weak solutions, sometimes what is difficult is to understand, okay, first, what do I need to prove uniqueness of these PDEs, okay, which are not trivial PDEs? How can I get the Dirichlet boundary conditions out of this? And this is what we call so in the particle system literature, this is what I call the replacement lemmas. So you need something, you have some, let's say, some observable of your dynamics that you need from that observable to recover fractional derivatives, boundary conditions, Dirichlet boundary conditions, how to do it. So let me just explain you how to do this in this case, and then I comment a bit on the other. Because for nearest neighbors, I said that what we had to do is to replace eta 1 by alpha. And then you would see the boundary conditions of Dirichlet type. So I want to show that, in fact, when I have the profile very close to 0, the profile is alpha. So this is what I said we had to do. And how do we do this? The idea is that at the microscopic level, you replace eta 1 by an average of particles in a big microscopic box of size epsilon n. And then when you have this average of particles in a big box, this is very close to your rho 0. Okay? Okay, so how do we do this? So we need somehow to transport mass, so let me call this point x and this point y. There we need to have an effective way of transporting mass from x to y. When we are in the nearest neighbor's case, there is not much to do, because if you want to take a particle from x to y, you have to do it by nearest neighbor jumps. But when you have long jumps, you have many ways to do this, and the question is, what is the let's say, the path that costs less. And so in this business, when we go to long jumps, the difficult thing is that since we are varying all these parameters, all the estimates have to be very precise. But the idea is that to make an effective transport of mass at the micro level, okay? What is the correct path in such a way that I can do this transport of mass and to recover whatever boundary conditions I have. Okay, I have 1 minute. So let me just tell you quickly. So I didn't talk about porous medium, but there is a way to get porous medium out of particle systems, which is quite nice. It's 1 minute or seconds. Okay, so for porous media, let me tell you quickly. You have this equation. Okay, maybe I use this. Imagine that you are doing this with a square, and you can write this in this divergence form in this way. So you see that your diffusion coefficient, the rho, goes to 0 as rho goes to 0. So the question is, can I have a particle system in which I can see this equation? And one that you can do is the following. One is described there. So it means that my particle system, particles will be blocked as soon as the density is low. So the idea is like this. You have an exclusion rule, and you ask particles to move if they have a certain number of particles close to where they go, close to where they are, or to where they go. Okay? And you say, well, so if I have a particle system like that, maybe I can define that if I want to jump from here to here, I should require somebody here or somebody here. And if I do not have these two guys, my rate is 0. And this you start to generate particles systems for which you can get the generate equations. Okay, so just to say that this can be done with boundary conditions as in the nearest neighbor case. We can actually do fractional equations given in terms of regional fractional Laplacians on unbounded domains with boundary conditions by putting, for example, a barrier. And, okay, just to finish, fractional porous medium as well, as long as you have long jumps, but you require particles to have someone close to them in order that you make the jump, and if you don't have, then you get blocked. Okay, and I stop here. Thank you very much for the attention.
Thank you very much for your beautifully timed talk. Okay, time for questions.
Yeah, it was you.
So for the mixed Robin condition, if kappa is in between 0 and infinity, what does your solution converge to?
Sorry, can you repeat?
If you have this mixed boundary condition, if kappa is in between 0 and infinity, what does the solution converge to? Do you have a characterization?
Sorry, I couldn't understand. I'm sorry. Can you talk louder?
If your parameter kappa is in between 0 and infinity, it's neither 0, it's not infinity. It's in between.
Sorry, I cannot understand. Sorry.
So did you ask a question about whether if it's not it's infinite the other boundary, or was that about it? Maybe I didn't understand. But it was about boundary conditions. So
if I can get what? Sorry, I didn't understand. I don't understand the question. Sorry.
If your kappa is in between 0 and
if I'm what?
kappa.
parameter that you are tuning is in between 0 and infinity, you have a characterization for the limiting solution.
Yeah, so kappa can be anything. Kappa can be any parameter that you can tune going to 0 or to infinity. And if you look at the solution for your equation with k, it goes to the solutions in the Neumann regime and in the Dirichlet regime. For any k. So this k is arbitrary, whatever. K is a parameter defined at the microscopic level that can be anything, but it only appears at the macro level in certain equations, not all equations.
I thought for k going to 0, you get like 1.
Yes, exactly. Yeah. So you take the solution, for example, in the Robin case, the heat equation with the Robin, with the k, and you take k to 0, and you get the heat equation with Neumann boundary conditions. And the k to infinity, the Dirichlet.
Can I ask one more question?
Yeah.
What about the higher dimensions, as you mentioned?
Yeah, this is a very good question. So it has been done. In the nearest neighbor case has been done. Long jumps, no, it's completely, it's something. So it's one of my future works. Higher dimensions, other domains. Hydrostatics, for example. Hydrostatics in long jumps case, we know very little. Fluctuations, so the same problem that he was describing, which still, okay, in fluctuations it's quite complicated because you might have, especially when you have systems with two conserved quantities, this is something I wanted to talk about, but I could not. Is that you start to see fluctuation fields living in different time scales, different velocities, and other boundary conditions. So the ones that I described, they are the ones that come from the integration by parts formula for the regional fractional Laplacian. But, I mean, others. This is something to look at in the future.
Okay, thank you. Anything else from the audience? Can you raise your hand?
Yeah, it's a very simple question. Do you know what happens at the boundary, but not at the boundary of the PDE, but at the boundary of your picture that you have between Dirichlet and Neumann boundary condition? What happens at the boundary?
Yeah, it's a very good question. So it's open. I hope I understood the question correctly. But for example, in this case here, for this model here, that we get this regional fractional Laplacian, one of the things that is not known, so what we can prove, so let me just go back. So one of the equations that we get has this weak solution, and we can show that the profile lives in some fractional Sobolev space. So we know that there is some regularity for the solution in the bulk, let's say in the interval 0, 1, which is Holder gamma minus 1 over 2. And one of the questions that people in PDEs still don't know how to answer is what happens at the boundary? What happens to the profile? What is the regularity of the profile, of the solution of this equation, when you are exactly on the boundary? So this is something that maybe one can try to use the particle system in order to give answers to this question, but we still don't know. No. So we don't know, the boundary is tricky, quite tricky.
Okay, in case there are no further questions, let us thank Patricia again.
Thank you. Thank you. Thank you.
Hi. I'm not sure you can hear me. Yes, so I would just like to finish by saying that it's really an honor to be in this conference. I'm really happy because I had a chance to give it live in Finland. So I hope you enjoyed it. And I really like to thank the organizers for doing it, to making this event possible, even in such a short notice. And I will be in this Discord platform. So in case anyone wants to ask questions about my work, and thank you very much for attending. Bye-bye.